All right, so we're in Unit 11 still, but now let's take a look at the equilibrium constant values and what that means with respect to how you're going to then calculate. So our equilibrium constant is supposed to show you that ratio of products to reactants. When you have a very, very large equilibrium constant, what that means is that you have a lot of products that have been created. We describe it as being favored. That means if you have a lot of products created, you don't have a lot of reactants that are remaining at the end of the equilibrium. This was when you would sit down and calculate stoichiometrically, where one of your reactants was a limiting reactant. We described that as the reaction going to completion because it appeared that we completely ran out of one of those reactants. However, if that reaction were actually an equilibrium type of reaction where it was reversible, it was in a closed system, and you had plenty of chemical present, then that reaction would return to an equilibrium. We never calculated that. Now we're going to start taking a look at that. A lot of the equilibria, however, have small values for K, where now there are a lot of reactants and not that much product. These are going to dictate how you then run your reactions and how you run your calculations. And that's the important part, is what does it mean and what's it going to mathematically look like? So we're going to take a look at some versions of equilibrium constants and reactions that you're going to want to familiarize yourself with for the remainder of this unit. The first one is known as KSP. So again, this is a value of K. This is a version of Kc actually, but this Kc is going to be specific to the solubility of an ionic compound. Let's use lead chloride as an example. So here we have lead chloride solid dissolving in water, and because it's ionic, when it dissolves, it's also going to dissociate. So you see here we have a lead ion, and we also have two chloride ions. That's our dissociation reaction. So when we write an expression, we're going to be writing again a Kc expression. The difference is going to be, however, that that solid will not appear in the denominator because it's a solid. So we're going to put a 1 in for that. The reactants, however, will appear in our numerator. So here are our reactants in the numerator. Now, you might remember from solubility rules that lead chloride is considered insoluble. And since it's considered insoluble, that means that the ability for it to turn into ions while being dissolved in water is really low. What does that mean? That means that this value of KSP is going to be a very small number, which means if you put in some lead chloride into solution, what you'll see is very little of it will turn into ions and a lot of it will remain as a solid. When that happens, you have reached your dynamic equilibrium. And not just that, but we've also reached what's known as saturated, a saturated solution where the maximum amount of ions can be dissolved in that amount of water. So when you've reached a saturated solution, you can then calculate KSP. But KSP can also tell you when you're going to reach that saturated solution. Now, the benefit of knowing a KSP and knowing that the reaction that involves a KSP is the dissociation of an ionic compound lets us also do the calculation in reverse, and that is being able to precipitate ions into an insoluble salt. So this is our reverse reaction. If we put something with lead, like lead nitrate, into solution, and something with chloride, like hydrochloric acid, into solution, what we would then see is that it would precipitate the lead chloride. Again, since lead chloride is an insoluble salt, what would happen is we would guarantee basically a precipitation because the value of KSP for lead chloride is so small that would mean that the inverse value of KSP would be really, really large. That means that you would be able to then calculate this with stoichiometry first, using one of our reactants as the limiting reactant, in order to identify how much solid you would precipitate and how much of the remaining reactant would be left over. Let's take a look at another one. So this one is known as the autoionization of water. And again, it's going to be a Kc value, mainly because it's going to involve aqueous solutions. So if you take a look, our ionization of water is one of two reactions. You're either looking at the first reaction, which goes along with the Arrhenius representation, or you're looking at the second reaction, which goes along with the Bronsted representation. So what does that mean? Again, if we relate our hydrogen to our hydronium concentration and just simplify it to a hydrogen ion, what we see is that we have this value. Again, it's a Kc, but we're going to put a little W there to represent that it's specific to the ionization of water. That shows hydrogen being multiplied by hydroxide. Notice the denominator is a 1 because water is a liquid, so it does not get involved in being placed in the equilibrium expression. However, we also know that the Kw, anytime that you're at what would be considered room temperature, 25 degrees Celsius, is going to have a value of 1 times 10 to the negative 14th. That's very small. And so we know that the value of Kw when water is turning into its own ions is really small. It doesn't happen excessively. It happens just a little bit, but it happens all the time. What does that then mean? That means the reverse reaction has some really important characteristics. So here's the reverse reaction. We're now looking at a hydrogen ion reacting with hydroxide to now make water. This is the driving force for any acid-base reaction that you might encounter, especially when you've got a strong acid and a strong base. The formation of water, which is this reaction, is also the inverse of Kw. So that means that instead of having a tiny 1 times 10 to the negative 14th value, we now have the inverse of that, a 1 times 10 to the 14th value. This is again why anytime you put a strong acid with a strong base, you are automatically always going to end up forming water because of such a large K value. Let's take a look at another two that are also related to acids and bases. The first one is known as Ka, which you might be able to guess is an acid dissociation equation, and Kb, which you might be able to guess is a base dissociation equation. Both of them have been written out for you. And again, the weak acid, the first one that I've given you is the Arrhenius equation, and the second one is the Bronsted. For the base, typically we're going to only be looking at Bronsted bases, so I've only provided for you the Bronsted base reaction. Again, we'll walk through each of these separately. So here is Ka, and the expression, again, we're going to assume that we're looking at hydrogen being identical to hydronium. So again, just for shortening purposes, you'll see that I've just placed in a hydrogen ion. At this point, we do not have a solid or a liquid as part of our equation, other than the water that you see here in the Bronsted version. The water is, of course, not going to be in our expression, so we have instead our hydrogen ion and our conjugate base, which would be the anion of the acid, and now we have a weak acid, which is dissolved because it's molecular. It's just not 100% dissociated, so it's now present as a molecule dissolved in the solution. This Ka is, again, typically small, and so because we have a small value for Ka, that again kind of dictates why our weak acid is a weak acid. There aren't a lot of ions present. However, when we go ahead and we place this reaction in reverse, what we now have is a lovely reaction that shows us that we could take a strong acid and react it with the anion to now form the weak acid. This is one type of acid-base reaction. And again, what does this mean? This means anytime an anion of a weak acid is able to react with a hydrogen ion that comes from a stronger acid, it's automatically going to form this weak acid. So again, we can invert our Ka expression and come out with a lovely means of calculating how much of our weak acid gets formed. Again, because it will be a larger number, a larger K value, we'll also be able to utilize stoichiometry and identify a limiting reactant. So finally, let's take a look at the base dissociation. Again, this is a Bronsted reaction that's being shown to you so that you can again see the hydrogen ion moving. And this then would look and appear as though it is in fact the exact same ion that you saw in the weak acid. And to a certain extent it will be, because it's going to be an anion that is able to accept a hydrogen ion. So oftentimes that will result in it acting as a base. This then provides for us a weak acid as it reacts with water, and also a hydroxide ion. So it will actually measure a pH that is basic as well. When you place this in water, that's automatically going to happen. And again, the only value that is not going to appear in our expression is going to be the water molecule. So our expression ends up looking something like this, where again we have a weak acid that is soluble in water but not dissociated. We have a hydroxide ion, and then we also have the anion that is reacting with the water. Again, this value that is known as Kb is going to be a very small number in most cases, which means that oftentimes you're going to have a nice equilibrium, pretty simple calculations. But again, what is the reverse reaction going to look like? So here is the reverse reaction, and what it tells us is if we have a weak acid and we can mix it with a strong base where only the hydroxide is really going to play a role, then we can actually react that weak acid with the strong base to form the weak base in water. Again, remember, the water formation is a really high value. We saw that above with the Kw being inverted. So in this case, that water is still going to play a nice role, and it's going to force this reaction to the right. Again, that means that you're going to end up with a nice large value for this K, which is really the inverse of Kb. So again, what does all of that mean? That means that when you're looking at any of these reverse reactions in which the value of the expression becomes large, in these cases, because we've inverted another value, all of them you're going to be able to actually use stoichiometry, straightforward, identify who is the limiting reactant, and then run your calculation. In reality, every single one of these reverse reactions is something that you've already done and already experienced, because all you've done so far this school year is work with stoichiometric calculations. So these are the ones that are going to be the most familiar, but now we're just putting a name to what that means. It means that they have really large K values. So at this point, we're going to be practicing with small K values and large K values, and what all of that is going to look like in terms of your calculations, and also practice that you're identifying correctly with either a solid that is dissociating, water that is ionizing, or the impact of a weak acid in water or a weak base in water.